Okay, welcome everyone. So let's continue our working with characteristic equations, finding eigenvalues and eigenvectors. And so let's consider, to get things going, a 2 by 2 matrix A where the first column is 4, minus 1, and the second column is 5, 2. And we would like to find the eigenvalues of this matrix. So let's just recall how that process goes. One way to identify these eigenvalues is to identify values of lambda that make the determinant of the matrix A minus lambda I equal to 0. So the matrix A minus lambda I is what we get when we subtract lambda from the diagonal entries, and nothing happens to the off-diagonal entries. So we want to calculate the determinant of the matrix now whose first column is 4 minus lambda and the minus 1, and the second column is 5, and then 2 minus lambda. So calculating the determinant of this matrix, it's 2 by 2. So we take the product of the diagonal entries, which is 4 minus lambda times the quantity 2 minus lambda, minus the product of the off-diagonal entries, which in this case would be 5 times minus 1. And we set that equal to 0 and try and solve the characteristic equation. So in this case, we can group our terms together. When we want to solve a quadratic, it's often useful to put it in standard form. And we need to solve the quadratic equation lambda squared minus 6 lambda plus 13 equals 0. So any values of lambda that satisfy this equation are going to be eigenvalues for matrix A. So we can try and factor this. However, we are not going to get very far in the factoring process. This does not factor. So instead, we try the quadratic formula, right, which I've written down below, which would be x is equal to, in the numerator, minus b plus or minus the square root of the quantity b squared minus 4ac, all divided by 2a. So my value for a is 1, so I put that in the place of a. My value for b is minus 6. So I have a minus 6 over here. And then I have a minus 6 squared, which would be the same as 6 squared. And my value for c is 13. So simplifying this quadratic formula, we would get 6 plus or minus, and then under the square root, we have a minus 16 because I have 36 minus 52. And that gives me a negative 16 over 2. So when we have a negative underneath this square root, if we're only considering real numbers, then we would say this matrix has no real eigenvalues. However, this characteristic equation does have complex roots, and so we're going to consider the complex roots of this characteristic equation as complex eigenvalues. And so before we go any further, I want to explain how we can handle things like square roots of negative numbers and just some basics about complex numbers before we jump back into the linear algebra side of things. So we define the imaginary number, which we denote I, as the number that satisfies the relation I squared is equal to minus 1. Which is equivalent if we take the square root of both sides, which is equivalent to saying that I is equal to the square root of minus 1. So this is what allows us to therefore make sense out of the square root of negative numbers by introducing this imaginary number that we denote I. And so, for example, in the previous characteristic equation, we needed to simplify a term that looked like the square root of minus 16. So underneath the square root, I can break that up into 16 times minus 1. And then we're allowed to break up products underneath the square root, so I can write this as the square root of 16 times the square root of minus 1. The square root of 16 is 4. The square root of minus 1 is I. So therefore, we say the square root of minus 16 is the complex number for I. And I just used a term that we haven't defined yet, which is complex number. And so a complex number is any number that can be written in the form a plus bi, where a and b are real numbers and I is the imaginary number. And so we often denote complex numbers with the letter z. So we would say z equals a plus b. I is a complex number. And there's two parts to this complex number. There's what we call the real part, and that's the part that does not have the I in it. So in this case, we would say that the real part of z is a. And we denote this RE(z). So this means the real part of z, and it's going to pull off the piece that doesn't have an I in it, which in this case is just the generic a. And then we have the imaginary piece of the real number that we denote with IMZ. So this means an imaginary part of the complex number z, and that's going to pull off the coefficient b in front of the I. So we would say b is the imaginary part of complex number z.